Imagine you have a state-of-the-art video diffusion model. You want to edit a single, highly specific video. The standard approach is test time tuning. You take the pre-trained model, feed it your source video, and let it adapt its weights in real time. It sounds like the perfect solution for personalized editing. But in practice, it consistently fails. The model either completely ignores your new editing prompt, or it blurs the entire frame, losing all localized control. Researchers at Tsinghua University recently identified exactly why this happens. They call it prior collapse, and they've built a framework called ElasticTTT to fix it. Today, we're going to break down the math behind why standard test time tuning breaks diffusion models, and how 3 precise interventions restore generative elasticity without sacrificing fidelity. To understand prior collapse, we first need to look at the fundamental mismatch between how diffusion models are trained and how test time tuning operates. Diffusion models learn by mapping noisy latents back to clean data across a vast, diverse distribution. They predict a velocity field that smoothly interpolates between noise and structure. But test time tuning changes the objective entirely. Instead of sampling from a distribution, you're optimizing the model on a single, zero-variance instance. Mathematically, your target distribution collapses into a Dirac delta function. You're forcing a highly parameterized network to memorize one exact trajectory. This creates 2 distinct failure modes. First, conditioning collapse. Because the model is repeatedly updated on a static source prompt, the pathways that process text conditions weaken. The network hardcodes the source video into its parameters and simply bypasses your new editing instruction. Second, spatial entanglement. As the model memorizes the global target, it stops extracting meaningful spatial representations from the noisy input. Semantic boundaries dissolve. Try to edit just the foreground, and the background gets corrupted too. Previous work tried patching this with low-rank adaptation, masked optimization, or attention map manipulation. But these are architectural hacks that require delicate tuning, often break temporal consistency, and still leave the underlying optimization dynamics vulnerable. ElasticTTT takes a different approach. Instead of treating these failures as isolated artifacts, it intervenes across the entire generative pipeline, from optimization to sampling. The root cause is that rigid Dirac delta target. ElasticTTT's first move is target distribution regularization. The core insight is elegant. Inject controlled stochasticity strictly into the optimization target while keeping the input trajectory completely clean. During flow matching, the model predicts a velocity based on a noisy latent. Instead of targeting the exact clean video, TDR adds a zero-mean Gaussian perturbation to the target. Crucially, because the noise has a mean of 0, the expected gradient remains perfectly aligned with the original video's true vector field. The global minimum doesn't shift, but the optimization dynamics do. By replacing the sharp point with a continuous local Gaussian manifold, TDR implicitly injects a geometry-aware penalty into the loss landscape. In mathematical terms, the gradient covariance matrix decomposes into the standard covariance plus a Gauss-Newton penalty, proportional to the squared Frobenius norm of the Jacobian. When the network tries to form a degenerate, stiff spatial mapping to perfectly memorize the source, the Jacobian norm explodes. The optimizer is physically ejected from these sharp minima via stochastic gradient noise. To converge, the network is forced to find a flatter, more generalized minimum. It retains its elastic denoising properties, instead of lazily memorizing a rigid spatial map. But TDR alone isn't enough. After tuning, the model's distribution still exhibits a residual shift toward the source concept. Standard classifier-free guidance, which usually just pulls generation toward the target, actually amplifies this bias. It's like trying to steer a car that's already stuck in a mud puddle by just pressing the accelerator forward. ElasticTTT solves this with contrastive classifier-free guidance. They reframe the problem using energy-based models. The overfitted model creates a localized energy well in the latent space, acting as a gravitational pull toward the source video. Standard CFG inadvertently scales this pull. Contrastive CFG changes the guidance formula to a tridirectional formulation. Instead of just contrasting the target against a null prompt, it explicitly contrasts the target against the source prompt itself. The modified velocity prediction becomes a combination of standard unconditional guidance and a semantic opposition term. By algebraically subtracting the source condition velocity from the target condition velocity, the method isolates the gradient bias field and cancels it out. This actively repels the sampling trajectory away from the memorized source distribution, restoring crisp semantic transitions and giving the model the freedom to actually follow your edit. Even with conditioning collapse fixed, spatial entanglement remains a threat during inference. The tuned network still struggles to isolate regions. Existing methods try to fix this by modifying attention maps or stitching in frozen background latents, which often creates visible seams or breaks motion coherence. ElasticTTT's third innovation is asynchronous noise scheduling. The key insight is that temporal uniformity exacerbates entanglement. If you evaluate the entire latent at a single time step, the network falls back on its memorized output. So asynchronous breaks the global temporal synchronization. Using a segmentation mask, the method assigns independent diffusion trajectories to edited and anchored regions. The edited area receives a high-noise regime, giving the model maximum flexibility to render new concepts. The preserved region is restricted to a low-noise regime, carrying maximum information from the source. These regions are updated asynchronously, spatially fused at each step. The model processes them with distinct time-step embeddings, forcing clear representational boundaries. It's a forward-pass desynchronization that naturally handles boundary interactions like shadows and lighting, without the hard artifacts of post-hoc blending. The results speak for themselves. Evaluated on the 1-2-1 architecture, ElasticTTT achieves state-of-the-art performance across quantitative benchmarks and VLM-based evaluations. It significantly outperforms both training-free methods and other TTT baselines. The framework is also highly robust to hyperparameter choices, with TDR and CFG scales showing wide effective ranges. Most importantly, it scales favorably. When applied to the larger 1-2-2-5B model, the performance gains are even more pronounced, proving that the method successfully unlocks richer generative priors that would otherwise be suppressed by memorization. Prior collapse isn't just a quirk of video editing. It's a fundamental tension between single-instance optimization and distributional sampling. ElasticTTT resolves it by respecting the geometry of the optimization landscape, actively canceling distributional shifts during guidance and decoupling spatial trajectories during sampling. This isn't just a patch for video editing. It's a blueprint for how we should approach test-time adaptation in any highly parameterized generative system. If you're working on personalized AI, fine-tuning at inference, or just pushing the boundaries of controllable generation, this paper is a must-read. I'll drop the link to the project page and code in the description. Let me know in the comments how you think this approach might translate to image generation or 3D diffusion. Thanks for watching, and I'll see you in the next one.